Welcome back. Hope everyone had a great lunch. We now have David Gao, who is a software engineer at Google who works on KUnit, a unit testing framework for the Linux kernel. He'll be speaking to us today on KUnit past, present, and future. Please welcome David.
Thank you. So I hope everyone has had a good lunch or appropriate lunch substitute for your time zone and has been enjoying the conference so far. As Andrew mentioned, and as you can probably guess from the slides, my name is David. I work for Google and I work on KUnit, which is fortunately what this talk's going to be about. So we're going to talk about three things: KUnit's past, KUnit's present, and KUnit's future, but not in that order. Basically, we're going to start off by talking about what KUnit is, what it currently is in the present. For those of you who were at LCA last year, you might remember Brendan Higgins giving a talk about KUnit then. So the past will be what's happened since then. And for the future, we're going to see what we can come up with, what you can look forward to for the future of unit testing and other testing in the Linux kernel. So let's get started. What is KUnit? So KUnit officially is a unit testing framework for the Linux kernel. We're a little bit hazy about what the exact definition of unit testing should be. No one particularly loves arguing over definitions, I'm sure. But basically, it's a framework for small self-contained tests within the Linux kernel. And by within the kernel, I mean KUnit tests are actually written as kernel code in C, linked into a kernel, and run. Unit testing, generally we mean small, fast, and self-contained tests. Think of, testing a single kernel function or even a single code path through a kernel function rather than some enormous integration test that, generates hundreds of files and checks file system performance or checks an entire system the whole way through. So generally, KUnit, lots of small independent tests. And the other thing KUnit does is it's an effort to basically standardize these tests. So what we have with things like K-self-test and that is lots of largely standardized scripts for running tests and a common output format. But KUnit provides helper functions and tools that make KUnit tests essentially automatically run in a way that is consistent and always produce format that is parsable by the same tools. The KUnit framework, and that's the other interesting word in a unit testing framework, basically means we have a set of helper functions that help you write tests, as well as automatic execution of tests on startup. And KUnit tests can now be built either into the kernel, in which case all the tests run at startup, or can be built as modules, which you can load and run tests, much as many existing kernel testing systems use. Finally, KUnit tests can be run under basically any kernel architecture. The KUnit framework itself is architecture agnostic, but we do provide tooling for running KUnit tests under user mode Linux, which is a kernel architecture that basically builds the kernel as a normal x86 64 Linux binary. And the advantage of this is that KUnit tests can be extremely fast. You can run your entire test suite in a matter of seconds rather than minutes or hours setting up testing hardware and the like. So what actually do you need to do if you want to find KUnit? KUnit, since 5.5, is now upstream. So you can find KUnit itself and the number of KUnit tests in the kernel you're probably running now. If you get the latest source tree from kernel.org, KUnit is there. You can enable KUnit just by enabling a kconfig option called KUnit. And there's also one KUnit all tests, which will automatically enable a whole bunch of tests written with KUnit that apply to your current config. So amongst that, you can pretty easily add KUnit to a kernel you've got. We also have a number of tools. KUnit tool, or KUnit.py is the main one, which is, as I mentioned, something that builds, configures, runs a KUnit user mode Linux kernel, and then parses and prettily prints all of the test results. If you're looking for the KUnit code, you can find that generally in the libkunit directory in the kernel, and that's where you will find the code for the actual KUnit helper functions, KUnit execution framework, etc. But tests generally sit just alongside the code being tested. So if you have, a file list.h, list.c containing, list manipulation functions, it'll often be in a list_kunit.c file. And if you build it as a module, you'll get a list kunit.ko module. So basically, the idea here is current kernel, you can find, and when you're writing tests, you can just put a test alongside your code, and KUnit will quite easily be able to run it. There's lots of documentation available for KUnit, which we like to think is at least not worse than the rest of the kernel documentation. It's, in the documentation directory, documentation dev tools KUnit, you'll find it. There's also a kunit.dev website, which basically is just a mirror of that with a few other things here and there. So one of the reasons you're probably here is wanting to know, how do you write a KUnit test? And KUnit tests basically are just a single function. So function accepts this KUnit argument as a structure, and this function runs some setup to set up whatever thing you're trying to test, tests it, and there are a bunch of assertion and similar macros that you can then run to verify that the resultant state matches what you expect. KUnit tests are then organized into test suites, which are a collection of related tests. It's just an array of these functions. And for example, you might have a subsystem, say ext4, and you might have a test suite for, ext4, within that tests for various functions within that. Similarly, could be something smaller. In practice, ext4 has an inode suite, so the test suite is ext4 inode, and within that there are functions like checking timestamps. So let's have a quick look at an actual test function. And basically what we have here is a single static function, pretty boring. It accepts this KUnit structure, which basically is just the context for the currently running test. And in this case, we're testing the list move tail function, which is part of the kernel linked list data structure. So, we set up two lists. We set up a couple of elements to add to those lists, add them. This is sort of the setup for this particular test. We call the function list move tail, which we're trying to test, which should result in one empty list and one list with element B in it, followed by element A in it, and then just use these KUnit expect macros to expect that the list is empty, list 1, and that list 2, its next pointers all nicely match up. And that's basically what a KUnit test tends to look like. You have some setup, some code you're testing, and then a bunch of these expect macros being called, which verify the result. Now, in the case of list test, we've got lots of tests for the list's data structure, not just for that one function. And the suite for that, just a basic array of, we have this KUnit case macro that describes an individual test case, and then you just put the function name through. So it's pretty easy to group these lists of tests. It's also possible, you can see we create a list test module struct, which is the suite, give it a name, give it the list of test cases. You can also, if your test has a lot of common setup or teardown code, pass a setup function and a teardown function, which will be common between all of these tests. So that's a rough idea of what a simple test looks like. Most KUnit tests will be a little bit more complicated than that, but not many and not much. So for the most part, you're again looking to test one function, maybe a couple of functions that work very closely together, sometimes even just one code path through a function. You might have a separate test for a function working successfully or a function working incorrectly and returning an error. And once you've got want to run them. There are, broadly speaking, two ways of doing this. You can either use the KUnit tool with script, which will run them under UML, or you can just build a kernel and enable them. When you're writing a test, you treat it as any other module. You just add it to the make file, kconfig file, give it an option. In this case, we've got config list KUnit test. And to use KUnit tool, you create a .kunit config file in the build directory of your kernel. KUnit tool defaults to a .kunit directory, and then include all the config options that you'll require. So config KUnit equals Y. You need KUnit if you want to run any KUnit tests, and config list KUnit test equals Y. If the thing you're testing requires other config options to be enabled, you're testing a particular driver, you will also want to add the config option for that driver in. Obviously, the linked list example, every kernel has the linked list data structure enabled. And then finally, once you've got that set up, you can just run this tools testing kunit run command, and magically everything will be configured, built, run, and then a parsed summary will appear. If you prefer to get the raw test output in the machine-readable KTAP format, you can as well. So this is what the raw tap output that KUnit tests give. On the left, we have a successful run of list test. On the right, we have a one which has failed. So basically what we have here is for the test suite, it starts off with this tap version 14 and then a count of the number of test suites. Our subtest is list. Within that, we then have, in this case, 36 list tests, and they're all just marked as OK. And so the final suite is also OK. For the case where it's failed, it basically looks the same, except one of these tests says not OK. And in this case, it then prints a nice error message saying, an expectation failed on this line. We expected list empty careful to be true, but it's false. And this way, you basically get a nice assertion error message for the case. And finally, if any test fails, the whole suite fails. And that way you can just look at the resulting sort of suite line and say, okay, I know there's something wrong with linked lists somewhere. I can dig in, okay, it's this particular test. It's probably this del init function that's failing. If you use KUnit tool, there's in a tiny font here, a slightly prettier version of that where it nicely colorizes, passed as green and failed as red and warning messages as this sort of amber orange color, and gives you a nice summary down the bottom of how long things took and how many tests ran, how many failed, how many crashed. It's relatively boring, but does make for a very quick way of getting test results. And what personally, and one of the main aims of KUnit is, because this is relatively simple and fast to run, you can write a few lines of code to try to fix something, rerun the tests, takes a few seconds, change another thing, rerun the tests, see if they've passed or failed. Unlike testing systems where you've got to boot up a whole machine, do things, testing is basically instant. And so it can become a much more integrated part of your workflow. KUnit has a few other neat tricks, some of which are new, and therefore we'll go into a little bit more detail when we talk about what's new later on. But KUnit also has a bunch of helper functions for managing memory and other resources. It's quite easy to write a test which needs to set up a bunch of things and then have all sorts of error paths for, if this allocation failed, if that allocation failed, free other things. KUnit, you can register individual resources and have them automatically cleaned up if the test fails, or if the test succeeds. There are also helper functions like KUnit, KZalloc, which will do an allocation and automatically register it to be cleaned up. One of the newer features is parameterized or data-driven tests. So it's now possible to have a test where you have the same bit of test code that runs repeatedly against different inputs. And this is useful if you've, say, got a hash function you're testing and you've got a set of sort of standard test vectors you want. You can just stick those in an array and have the same test run against all of those. And KUnit will automatically tell you which input failed. You can do things like describe them. We'll get into this in a bit more detail later, but it's a very useful feature. There are also a number of other small things worth knowing if you're writing KUnit tests. These expect macros have some interesting variants. There's a string equals one, which will actually do the full string compare. There are message ones that let you pass your own messages if they failed, which is particularly useful in the case where you have a named description of some data that you're testing. If you're doing date time zone stuff, you can, instead of saying failed on this Unix timestamp, you can have next to it failed on leap year on midnight sort of things. And finally, KUnit also does provide its own logging macros that will output any log information in a format that the TAP standard approves of. And which will show up both in the kernel log and in a test-specific log in debugfs if you've enabled that feature. So that's a very quick overview of KUnit as a whole. Please, if you haven't tried KUnit before or you're interested, do check out the KUnit website and the documentation in the kernel. There are also lots of example tests. We'll go through a few of the tests that have been written over the last year shortly. But hopefully that's given you a very quick taste of what unit testing in the kernel broadly looks like. And what we're now looking at is the sort of past section of the talk. What's changed in the last year? KUnit only got upstream in 5.5, which was just over a year ago. And so what was then this very basic, you can write a test, it will run, has now had several additional features added and a frankly terrifying number of bugs and other issues fixed. I'll go over all of these one by one, as a few of these are quite interesting and useful. But if you've played with KUnit before, these are some of the things that you might not be aware of if you haven't looked at it recently. So the first here is module support. And thanks to Alan McGuire from Oracle for writing this and a few other features. This basically, KUnit tests originally were always built into the kernel, always run at startup. Now you can build KUnit tests as modules and load them at any time. This really has two big advantages. KUnit tests, now behave a little bit more like tests in a number of other test systems. A lot of people testing the Linux kernel have done so by loading test modules. And this is basically KUnit's equivalent of loading a test module. It works exactly the same way. It spits out this KTAP format, which is basically what self-tests spit out as well. So it's a much easier way of integrating into existing systems. And the other really useful thing is that there are a number of things that you might want to test which require a user mode context, there to be some running user space process. And when a module's loaded, mod probe is that. But in KUnit without module support, KUnit tests run early enough in the boot process, there's no userland running. So any test that might want to touch userland, and I wouldn't recommend tests do so if they don't need to, now can do things like you can test things that require copy to from user and other memory management things that expect there to be some user context running, which only currently works as modules. And one example of that, which we'll get to in a minute, is KASAN, the kernel address sanitizer, has some tests which could not work because they do require copy to from user. And hopefully module support is something that will allow some of those eventually to be ported. Another new and useful feature is named resources. So as I mentioned, KUnit can have individual test resources that are automatically cleaned up. A new feature is the ability to have named resources that are associated with the current invocation of a test. And this is a good way of passing test-specific information to other subsystems. Again, our KASAN tests are using this as a way of having KASAN understand A, that a test is running, and B, that it might be expecting some particular thing that's not normal. So we can have a KASAN context added to a named KASAN resource, and other parts of the kernel code that needs to behave differently when under test can pull from that. It also just can be useful as a way of storing resources in your own test code if you don't want to have to pass context through your own functions. One of the existing resource framework, you could create resources, but then it was up to you to keep track of a pointer to them so that you could use them. Now, any of your code, you can just pull a resource by name. One other thing which we'd wanted to have in the initial version of KUnit, but was a little bit too complicated to get working across all the architectures initially, is this concept of a KUnit executor. The first version of KUnit from a year ago, all tests were just run at init time as their own init calls. There was no part of the kernel that actually knew about all of the tests that were compiled in and running. And now there is this executor that loops through all of the test suites, runs them all. KUnit now actually knows how many tests there are. It can print out the correct count of tests, which previously didn't exist, so all the summary lines in the output work correctly. And it just makes it a little bit more of a standards compliant and simpler architecture for future feature work. As I mentioned a couple of times, KASAN integration, the kernel address sanitizer, for those who aren't aware, is a feature which basically acts as a sort of Valgrind address sanitizer for kernel memory accesses. It validates every single memory access by using an instrumented kernel binary. And if there's any attempt to access invalid, unallocated, otherwise poisoned memory, it will fail. And this, helps you find out of bounds on array accesses and all sorts of things that C code loves to do when you weren't expecting it to. And because KUnit tests are going to be exercising a lot of parts of the kernel in a very predictable way, being able to run KUnit tests under KASAN is important. And now with the integration we have, KASAN errors will automatically cause any running test to fail. And this way you can quite easily pick, this particular linked list test failed, it must be scribbling over memory somewhere, or something like that. You do have to be a little bit careful around, there's a KASAN multi-shot command line argument you need to set to stop KASAN from just panicking the kernel as soon as there's any memory error, which is definitely what you want in most cases. But if you're, want to you can actually get several failures all printed out in a nice tap format. Finally, a lot of KASAN's own tests have been ported to KUnit, which is a good test of some of KUnit's features, as well as being a bit more standardized than KASAN's previous testing regime, which involved just loading a module and manually checking to make sure the results matched what was expected. Not all tests have yet been ported. Again, some need access to user memory, stack traces under RCU and the like, which KUnit as a framework doesn't yet make easy, or does not, correctly plumb through, is a test running through, RCU calls and the like. A lot of nasty asynchronous stuff there, but it's great progress so far, and I think has made most of the KASAN tests much easier to quickly check for results. The parameterized testing feature that also was mentioned earlier is this way of running the same test code with different inputs. And this is, again, very, very useful. We've used this a few times already in the ext4 inode test. And I know Marco is looking to port the KASAN, kernel concurrency sanitizer tests, to use this as well. This basically, you create a generator function that generates a series of parameters. And then the test code will keep running until the generator function alerts it that there are no further arguments that need to be passed. This means that you can now actually run a number of tests which are not known at compile time. So if you want to run an absolutely absurd number of tests, you can. If you wanted to, say, check a maths function under every possible 32-bit float, you could. I'm not sure I'd recommend it, but it's possible to now run a test billions of times and have that work. But the main use for this is what we sometimes call table-driven tests, where you have an array of test vectors, nasty times for checking timestamp conversions of leap years and the like, or test vectors for hashing functions, or a series of known, compressed, decompressed inputs. Anything that involves format conversion, this is very useful for, or if you've got a big list of edge cases for something, known inputs and outputs, you can just have this as some data, and KUnit will run the same test code however many times. You don't need to do your own loops. You don't need to put anything special in to describe each thing. KUnit will run it, treat it as one big test, but tell you which inputs it failed on, if it failed on any. And the other feature this has, which you can see a bit in the example code here, is there's the ability to pass a description function if you have a table that has an element for a description of that particular test input. And that way you get a ability to say, as I mentioned, instead of failed on this Unix timestamp, you can say failed on midnight 1st of January 2000 or something. And there are series of things like KUnit array param, which you just pass test name, pointer to the array, and a pointer to potentially this description function. Bam, that's your parameterized test sorted. One of the major goals for KUnit, both in the last year and going forward, is to integrate with continuous integration systems. And the goal here is basically to make sure if you write a KUnit test for anything, then we can effectively guarantee that that code won't be broken by new changes, because anyone writing new changes should in theory be running these tests or have these tests automatically run on their behalf. And in that case, there will, if they've broken a test, we should know about it before that, ends up in a stable kernel or something. So that's the goal. And there's been a number of pieces of progress towards that goal. The KUnit, both config system and tool, have new ways of running all tests. The aforementioned KUnit all tests config option basically will enable all tests that have satisfied dependencies. This is really useful if you either have a kernel for some device you've already got your config for, or a distro kernel or something. You can just enable KUnit and KUnit all tests, and it will automatically enable basically every relevant test for that config. If the dependencies for the test are satisfied, the test will be enabled. And that's very convenient for people who want to run all of the tests. There's also this KUnit.py run all tests option. As KUnit.py is based around user mode Linux, this basically just uses make all yes config for user mode Linux to run as many tests as is possible. UML tends to have some breakages with obscure drivers, which we've started catching with this. So at the moment, there's still a list of broken configs we're slowly going through, trying to fix up so that this works in all cases with all drivers. But this is effectively our way of please test everything you can, enable every driver you can, and run as many tests as it's possible to. Unfortunately, the actual idea of running every single KUnit test is not all that well defined in any individual invocation, because it's possible that you've got two conflicting things which each have tests. But this is a drastic improvement of just having to remember the names of all the tests and manually write them into a config file. And then there are two existing continuous integration systems for the kernel, which KUnit is integrating with. Kernel CI, now we're well underway getting KUnit integration into that, so that will run the UML all tests as a new type of shell test. This is working. It's not fully upstream and enabled yet, but this will basically mean kernel CI will soon on various trees be running continually this set of KUnit tests, which include every driver we can find, and reporting any test failure. The other thing, which thanks a lot to the folks at Linaro for doing, the Linux kernel functional testing project is now also running KUnit tests instead of under UML on ARM and x86-64, and reporting KUnit test failures as a part of their test results there. And this is very exciting. We've already seen, the fact that KUnit tests, amongst others, are passing, as part of things in, tested by tags on stable kernels. And this also is including all of the KASAN tests, which, due to KASAN not yet working under UML, would not show up under KUnit.py. There are a number of other miscellaneous tooling updates. KUnit tool supports running all of these subtasks like building, configuring, compiling, running kernels, and then parsing the results as separate tasks. Previously, it was just one monolithic script that did them all. The really convenient thing about this is it now means you can use the tool's parser and pretty printer of summaries as a way of very quickly getting a summary of tests run by other methods. So if you're, instead of using KUnit tool to build a UML kernel, you're using QEMU, you can just pipe the kernel log to KUnit.py parse, and you'll get a nice summary of all the KUnit tests there. Equally, you can, if you're running a kernel with KUnit on an actual physical machine, within that, you can copy KUnit tool over to that machine and run KUnit.py .py against the test results in Debugfs, and you'll get a pretty summary for that test there. KUnit tool also now outputs JSON format in the kernel CI test output format. This is quite useful for the kernel CI integration mentioned on the previous slide. And another quite big change, particularly for people who've been using KUnit a little while ago, and particularly KUnit tool, is that a number of the files it reads have been shifted around a bit so it no longer pollutes the source directory. It now defaults to putting everything in a separate build directory, which by default is .kunit. KUnit config files are now called .kunit config files and now live in the build directory instead of the source directory. And this basically means even if your source directory is read-only somewhere else, or you just don't want to pollute it, you can quite easily run KUnit tool against any source tree, and you're not going to mess anything up. KUnit's now much safer to just try and run, and it shouldn't cause any issues. And finally, but I don't think least, we've gone through, and thanks to the enormous amount of community input you usually get for these sorts of bike sheddy discussions, we now have new naming guidelines for test suites, test modules, etc. And this basically is a way of standardizing, if you have a driver, what should its test module be called? Fortunately, everyone was eventually able to agree there, and we've got what I think is quite a good way of making sure that it's easy to find tests. And finally, we've got a lot of new tests in a lot of areas. There's power management, quality of service tests for parts of the power management subsystem, multipath TCP. There are tests for the crypto stuff there, which have been ported to a KUnit token systems. The kernel address sanitizer, the kernel concurrency sanitizer, both have KUnit tests. Some of the bit field manipulation helper functions have tests. Command line parsing for the kernel command line, there are tests for that. Thunderbolt USB 4, some tests, some stuff for managing IO ports and resources. That's just a very small, very quick list. But KUnit tests certainly have picked up drastically in the last year. And it's very encouraging to see people starting to play with this and write these tests, or port existing tests that were doing their own ad hoc things and just printing their own summaries in whatever format they like. And finally, what's happening in the future with KUnit? And the biggest thing is mocking hardware testing. This is probably the hardest problem that any sort of testing framework for something as complicated as a kernel and as low level as a kernel has. Testing drivers is really hard because you need some way of getting in and intercepting reads and writes to the hardware, preferably in a way that doesn't tank performance, because kernel people really don't like performance being tanked. There are several different ways we've been looking at to approach it. The simplest thing for KUnit is just to say, look, refactor your code to always allow some way of intercepting these things. Have it accept a function pointer, an ops struct, some interface that we can inject a fake one in. This is still probably the best way of doing this if you can, but obviously it won't work in every possible situation. Similarly, a way of forcibly intercepting functions is probably the most desired feature, and a lot of people who've been playing with KUnit, certainly internally at Google and elsewhere, have wanted a way of being able to say, oh, I want to, intercept KZAL or intercept, VMAP or something and fake that out when it's run in my test. This is obviously dangerous. You don't want to just replace important kernel functions. So finding a compromise of how much to support this and how much to find other ways of doing things is one of the big challenges. I would certainly appreciate people's input on that. And finally, a way of intercepting accesses to platform level I/O memory and similar would be very good. In the past, we've tried experiments of different mocking frameworks, class mocking for structures full of function pointers and things. There's an RFC of that available. You can find the function mocking I mentioned and the platform mocking of implementing stub interfaces. We've played around with a few of those. They're in ancient branches on Git repositories linked to on the KUnit webpage, but not really at a position that I think they're ready to be used yet. Function mocking, again, in particular, we've experimented with weak linking. People have suggested ftrace as the way of doing that, but you've got to be very careful. And I don't think whatever we do there will be something we'd recommend people doing if they have a chance. Another thing that we're looking forward to adding is the ability to skip a test at runtime. It's there are some circumstances where a test really shouldn't be passing, really shouldn't be failing, because some fundamental assumption that it makes isn't true. Like you're trying to test some multi-core system and you're on a system with only one processor. The correct thing to do there is not for the test to fail or the test to pass, but for it to be skipped. The KTAP output specification we're following has support for skipped stuff. We've got a prototype for this. It's something that we should be adding soon. And we have a large number of bug fixes and tooling improvements that we're looking at. Where the KTAP format's not fully standardized yet. Tim Bird's been looking at that a lot from the point of view of K-self-test. We want KUnit and K-self-test to output formats that are mutually sort of parsable and compatible. And part of that will involve reworking the KUnit tool parser to better support non-KUnit tap output. We want improved tooling for being able to test individual subsystems. One thing we'd really like to have is for a way for subsystem maintainers to be able to say, hey, if you're sending patches, please run these tests, and have tooling that makes it easy to just say, oh, you can run, kunit.py run fs/ext4/kunit config, and it'll run this predefined list there. And more generally, even outside KUnit, a way of specifying the testing maintainers expect, maybe an extra list of instructions in maintainers or a test script or something, and be something that a proposal we'd like to put together and bring to the community. And finally, we'd just like to improve the tooling for running non-UML based KUnit tests. And with that, because we're dangerously low on time, any questions or comments? I'd be happy to answer any of those.
Thank you, David. We've got time for just a small number of questions. First one, how flaky have KUnit tests been in practice?
So KUnit tests have actually not been flaky at all, certainly upstream. We've seen very, very few failures, and all of them, I think, we've been able to link back to an actual issue somewhere. There have been, I know a few people who've been using KUnit internally have broken things, like particularly under UML, which is not used a lot by anything other than KUnit. So people doing their own patches there have hit issues with the KUnit system as a whole, but individual tests haven't been flaky.
What's your favorite bug that you found?
I know there was trying to remember, there was something to do with was it scheduling? Or I'll have to get back to you on the detail. There was a really nasty bug involving memory not being freed at the right point, I think.
All right. Well, this brings us to the end of the time slot. So if you've got further questions, go on over to the Kernel Miniconf BOF channel and post them there. And otherwise, we will see you in 10 minutes for the next talk. Thank you very much, David.
Thank you.